Hi everyone, I am Polash Kumar Bora. Today I'll be talking about different types of function. And at the very beginning, I would like to apologize for not uploading the videos on a regular basis. I'm extremely sorry for that. And from now onwards, I will try my best to upload the videos on a regular basis. And these are the contents that I will be discussing today. And those are functions, different types of function, then composition of function, binary operation, and after that I'll be going for solving some of the problems related to the topics which I have told you. Okay, let's start the video. I'll be talking about different types of function. Okay, before going to different types of function, let me give you the definition of function. Already you got it in your first year course, and let me revise that one first, then I'll be going to different types of function. Let us try to understand what is the meaning of function, and this is the definition. The definition says a relation R that is going from A to B is said to be a function if every element of A is connected to one and only one element of B. And let us try to understand this concept by taking help of the Venn diagram. I think in that case it will be more clear to you. Suppose I have two sets. This one is set A and consisting of these elements. Another set I am considering. Suppose it consists of alpha, beta, and gamma. Suppose 1 is connected to alpha, 2 is also connected to alpha, and 3 is connected to beta. Now, whether every element of A is connected to one and only one element of B is satisfied or not, let us try to see. Every element of A is connected, fine, no problem is there. Whether these elements are connected to one and only one element or not, that is also satisfied. If you see one is connected to only alpha, 2 is connected to only alpha, 3 is connected to only beta. So both the conditions are satisfied. That means we can say that this is a function. Let me consider another example. This one is A, this one is B. It consists of 1, 2, 3, and this consists of alpha, beta, and gamma. Suppose 1 is connected to alpha, 2 is connected to beta, and 3 is connected to gamma, and 2 is also connected to gamma, suppose. The question is whether this is a function or not. The first one is every element of A is connected to the element of B, that is okay, no problem. But the second condition is violated by the element 2. 2 is not connected to one and only one element of B. It is connected to two elements. So this is not a function. Let me consider one more example. Suppose A is 1, 2, and 3, and B is alpha, beta, and gamma. Suppose 1 is connected to alpha, 2 is connected to alpha again. Now the question is whether this is a function or not. Again, this is not a function. Why? Because every element of A is not connected to the element of B. The first condition is violated. So this is again not a function. Let me talk about different types of function now. The first one is one-one function, and the second one is onto function. First of all, let us try to understand what is the meaning of one-one function. It can also be said to be as injective function. And here is the definition. A function f that is going from x to y is said to be an one-one function if the images of distinct elements of x under that function f are distinct. And this is the mathematical statement. F of x1, this is equal to f of x2, and this implies x1 must be equal to x2, and this must happen for all x1 comma x2 belonging to the domain. And the equivalent statement of this is x1 that is not equal to x2. This implies f of x1 is not equal to f of x2, and this must happen for all x1 comma x2 belonging to x. And both these statements are equivalent. Any one of them can be used. Okay, let me talk about onto function now. This onto function can also be said to be as surjective function, and this is the definition that you can see. A function f that is going from x to y is said to be an onto function if every element of y is the image of some element of x. And let us try to understand this concept by taking help of the Venn diagram. Suppose I have a function and that is going from x to y. It is said that every element of y, let me consider one arbitrary element in y. For this element, there must exist element in x such that y is equal to fx. Mathematically, we have for y belongs to y, there must exist x belongs to x such that y is equal to fx. Okay, clear? Just now we learned about onto function. This onto function can also be defined in some other way. It can be defined in terms of range of a function, and the definition is a function f that is going from x to y is said to be an onto function if the range of that function is equal to the whole codomain. And let us try to understand. Let me consider one example, then it will be clear to you. Suppose I have a function that is going from x to y. Suppose I have this 1, 2, 3 here, and alpha, beta, and gamma. Suppose 1 is connected to alpha, 2 is connected to beta, and 3 is connected to gamma. And this one is known as domain, and this y is known as codomain. If range of f if I talk about range of f, then it is nothing but is alpha, beta, and gamma, and this is equal to y, that is nothing but codomain. So if range of f is equal to y, then we say the function is onto. I think it is clear. Let me consider one more example which is not an onto function. Suppose I have a function going from x to y. It consists of 1, 2, 3, and it consists of alpha, beta, gamma, and delta. Suppose 1 is connected to alpha, 2 is connected to beta, and 3 is connected to gamma. Then if I want to write the range of this function, range of f, that is equal to, we have to collect all those elements from y which are connected to the elements of x. And if you observe, and those elements are nothing but alpha, beta, and gamma. And this is not equal to y. So in this case, our range of f is not equal to y, so the function is not onto function. I think it is clear to you now. Let us now try to understand the concept of bijective function. And let me first consider the definition, and you can see the definition that is given on the screen. A function f going from x to y is said to be a bijective function if f is both 1, 1 and on 2 at the same time. Let me show you by taking help of one example. Suppose I have a function and that function is going from x to y. Suppose 3 is connected to alpha, 1 is connected to beta, and 2 is connected to. And if you see the elements of x, these elements are connected to y, and there is a 1, 1 connection between the elements of x and y. Okay, so f is, and also let me calculate the range of f, and this is equal to y. From here, we can say f is also on 2. So from these two, we can say f is a bijective function. Okay, clear? I'm gonna speak about the composition of function now. It is very important concept that needs to be understood by every student. And here you can see the definition that is given on the screen. I'm giving you time to see the definition. Okay, let me explain now. To define composition of function, I need one condition, and the condition is that I have to consider two functions first. Okay, what is that condition? Codomain of the first function must be same as domain of the second function. And if this is the case, then we can define z dot f. And it is nothing but z dot f of x is equal to z of fx. And this is for all x belonging to the domain. All right. Let me explain by taking help of the Venn diagram. The function f that is going from a to b, and this is a function that is going from b to c. Then we have this z dot f. For x belonging to a, we must have an element y in b, and for y we must have element in z. How is it defined? You see, for x we have f of x here, and for z we must have z of y here. And if this is the function, then for x we have z here, so we can define z as z dot f of x. If I combine all these things, whatever I said now, z dot f of x, and this is equal to gy, and g of, in place of y we can write fx. So from here we can say z dot f of x is equal to z of fx, and it must happen for all x belonging to a. Okay, okay, I think it is clear now. Now I'm gonna speak about binary operation, and let us try to see the definition first. And this is the definition that is given on the screen. Okay, let us try to understand now. As in the definition of function, we have seen that for an element in a domain, we must have element fx in the codomain. For x, we must have fx here. In the same way, if we want to understand the concept of binary operation, and the function is going from this A cross A to A, and obviously the element here is of the form of ordered pair. In the same way, here you see, again let me repeat, for x I have fx here. For a comma b I must have star of a comma b here, star of a comma b here. And instead of writing this way, we'll not be writing in this form, we'll be writing star of a comma b as a star b. And let us try to understand this concept by taking help of one example. Suppose I have a binary operation plus, and that is going from R cross R. Then we generally used to write 2 plus 3 and this is equal to 5. What does this actually mean? Plus of 2 comma 3 and this is equal to 2 plus 3 and this is equal to 5. This is the actual meaning of this binary operation. I am going to solve some of the problems related to the topic which I have discussed. Let me consider the first question. Prove that the function f, that is going from real number to real number, given by f of x is equal to twice x, is 1, 1 and on 2. And here is the solution. You can see that the function is going from R to R and it is given by f of x is equal to twice x. First we'll be checking f is 1, 1. For this we'll be considering two elements in the domain such that f of x1 is equal to f of x2. This implies if I'm replacing this x by x1, this must be replaced by x1. So f of x1 becomes twice x1, and in a similar way, f of x2 becomes twice x2. This implies these two get cancelled out. We are left with x1 is equal to x2. Therefore, f is 1, 1. Now we'll be checking f is onto. And this is the Venn diagram for this problem. And for onto function, we have to consider one arbitrary element here. For this, there must exist one element here such that y is equal to fx. Let y belongs to R, that means this one is arbitrary. Now let me consider x is equal to y by 2. If y belongs to R, that means if y is a real number, y by 2 is also a real number. Now f of x is equal to twice x, and this is equal to twice x means y by 2. Get cancel out, this is equal to y. Therefore we have, for any y belongs to R, there exists x belongs to R such that f of x is equal to y. Therefore f is onto, and this is our answer. I'll stop here. In this video I have only solved one problem. In my next video lecture I'll be solving many more problems related to the topic which I have discussed here. And if you have any kind of queries, you can ask me or you can comment me in my comment section.